Okay, thanks everyone and welcome. So in this tutorial we're going to build an image viewer app in Makepad. And the goal is that we familiarize ourselves with the framework and build the app. So in this tutorial you'll see that we're building a slideshow with an image grid and show all the mechanisms of how that functions. And at the end there will be the integration with Makepad being shown, where AI LLM is integrated and an image, you can connect to an image generator to generate the images that show up in the image grid. All right, so building a minimal app. I put this at the top of the tutorial because it is essentially a repository that contains every step that we're going to go through in the tutorial. So if you don't want to type every single thing that I show, it is a good idea to clone this repository. Also, I included the 3 lines at the bottom, which compiles the last example, and this will cache the Makepad framework that is included in the examples. So that is pulled in over Git, so it might take a little time. So yeah, when this runs, then you know you can easily follow the tutorial. So if you're on Linux, you need to install a few extra dependencies. These are the libraries that Makepad framework needs to for instance, connect to the audio layer or the cursors and stuff like that. Of course, I assume that everybody has Rust installed and Git installed. If you need to install Rust, you can do this on Linux and on macOS. If you're on Windows, you need to go to the Rust Up site and download the executable and install Rust. It takes a little while because it also needs the Visual Studio tools. But yeah, this is a Rust tutorial, so I do assume that you have a working Rust installation. So, building a minimal application. So every application needs a window on desktop, and without a window we could not display our UI. So the first goal is to build a minimal app with an empty window. So this is going to be the result of this step, an empty window. This is a manual way of setting up the project structure. You type cargo new image viewer. That creates a directory with a cargo.toml and a main.rs. This is the way to create a new Rust project, or a very basic way. And the cargo.toml file contains this information. So the main.rs is empty, and if we can put a println, that means print output to the console, into that file, we can compile it. Hold on. Right. So Makepad applications need one thing extra, but let me see. Yeah. So normally in Rust you would have a main function like this, but Makepad has something called an app main function. And the reason that is separate is that Makepad also compiles to WebAssembly and to iOS and Android, and on those platforms you don't have a main function. Main function is for an executable, and if you are a DLL or a dynamic link file, so as you are used on web and on iOS and Android, then you don't have a main function, and you need to do all sorts of stuff in the platform to create and run your application. So for Makepad applications we have a special function called app main. So we're going to make an app.rs in the directory. It's going to look like this. We're going to have a source directory with an app, a lib, and a main. The main calls, in this case, I had to edit it a bit, but you call image viewer app main. In this case, it says step 1.1 because I had to name them differently because I have so many of them. And then that calls app main. So you can run this, and then you'll see hello world. So this is the first step of setting up the app structure for a Makepad application. Hold on, there's my example. So in Rust, you have to include your modules. In this case, we do pub/mod app to include app.rs in the structure. So again, you saw that I used step 1.1 because I have a different name for image viewer. If I would have used the same one, I couldn't differentiate which library it is. So if you're just building the single one, you call image viewer. Okay. That must be a typo. Right. We're also going to need a resources directory, and this is not Makepad, this is Makedeer. There we go. Now it makes sense. We're going to make a resources directory, and the resources directory is going to contain icons and other files that we use in our UI. Let's check our progress, and as you've seen, if you run cargo run -- release in the console, in this case, this would be here. This is the image viewer repository. I'll go to step 1.1, cargo run release, hello world. This is step 1.1. So now we have the basic structure of running, in this case, a console application, but we have added the basic structure for a Makepad application, which is the app.rs file and the resources directory. So, yeah, this is working so far. We have Sebastian as well, who can walk around and help out. If you have any questions, just stick up your hand and someone will come over and help you out. All right, now we're going to create the actual window, the graphical application. This is so far a terminal application, and now it'll become a Makepad application. So we're going to add Makepad as a dependency for cargo. We're going to use our DSL to define and style an app, and how to create the app struct. This is a little bit of boilerplate, so it's probably nice to just cut and paste it from the file tree, but I'm going to go through it to explain it to you. So first off, we're going to add Makepad as a dependency in your cargo.toml. So this file, we're now at step 1.2. You have Makepad widgets, which is the top level crate that contains all our widgets. Below it sits Makepad framework and all these other crates. But in the case of this dependency tree, you just depend on Makepad widgets. And in this case, I have set a Git URL. We also have a version on cargo. You can use 1.0.0, but we did some bug fixes in the GitHub repo, so it's faster and easier if you depend on the Git repo like this and use the dev branch. So now we're going to add the code that is an empty Makepad window, and we have to replace the code in app.rs with this block. This is still a bit of boilerplate, but it is not as much as it has used to be. It is structured in the following way. We have a use at the top that includes our Makepad widgets crate. Notice the star because it's a lot of stuff, so it would be impractical to include everything separately. And then we get a live design block. This live design block you have to see as not Rust. This is not Rust code. This is our UI styling DSL that allows you to, almost like HTML, structure your UI components. And it has its own use block. In this case, it is including all of the widgets that we have in our framework. Then we define the abstract. The abstract is, you can name it whatever you want, but the abstract is where your state lives. So every application has one instance of this struct. And we set on the root the UI reference, which is a widget reference. And as you can see, this UI assignment matches this field. So you can imagine that the UI engine spawns up this UI and stores the reference on this field. So, and then we have two things that we need to do. We need to implement two traits for the app struct. We need to implement live register, which is essentially a dependency loader for your app. Because Rust doesn't really do globals, this is the entry point that runs before your application is constructed so that you can include dependencies. In this case, it includes the Makepad widgets DSL code that is stored in the Makepad widgets crate. And then finally, we implement app main for app, which has a handle event function, and that handle event function calls straight into UI.handleEvent. Makepad applications are essentially entirely immediate mode, so that means that there are no random calls into your UI structure. Every event, mouse, render, everything that happens comes into this top-level function of your application, and then it cascades down into the UI. And finally, we're calling the app main macro that is generating now the app main function that you saw in the last example, because that app main function needs to do a lot of stuff, like creating a window, creating different entry points for different platforms. So we made it a macro, so you don't have to type it. So let's look at what that does when we can run it. Cargo run release. It'll rebuild. Luckily, it doesn't take that long to rebuild because we took a lot of effort to make Makepad compile fast. So here we have our empty window. I might also start using Makepad Studio. You can, I don't advise you to try it yourself right now because it's a bit of setup to get all the steps in here. But I can run steps inside Makepad Studio, so I don't have to mess with Windows. So I can do that as well, but I don't know. Maybe I'll just stick to doing exactly what it says here in the tutorial. So now we have an empty window, and yeah, this is a bit of the explanation that I just gave by looking at the code. Again, maybe for a quick recap, the live design macro defines the DSL for our UI, and here something special happens. You see app is two curlies and then app. That is actually the way the DSL connects to your Rust code. This expands to essentially a type ID on a class and a connection to a factory function. So when you see these things in our DSL code, if you look in our widgets library, this is a way to connect this Rust object to the DSL object. Since this is not Rust, it's an important connection. And here then, to explain, we make a root component. Every application starts with a root component because you can have multiple windows, right? You can have any number of windows you want. And then we create a window, and the window has a body, the body of the window, and then we create a view. And a view is essentially our div compared to HTML. It's a general container that can have any number of child elements and that can have styled backgrounds and so forth. Yeah, again, the abstract. You can see that there's two derives on it. There's derive live and live hook. These proc macros, they generate all the glue between the Rust struct and the DSL. So they're very important. If you forget these derives, it just does nothing. It doesn't work. So we have the live trait that essentially generates the the glue code. So here you see the UI, right? And here you see the Rust version. And so the live attribute here says that this field can come from the DSL. So the DSL creates a connector to that field using these attributes. And we also have a Rust attribute. If you do that, then that means don't touch this attribute. This attribute is completely for Rust code only, and it is not used by the DSL. So the live hook trait that we see here, live hook, right, we derive it. The live hook trait implements the way to hook into the life cycle of the DSL. We're not going to look at that right now, but it might come up later. And the live register trait is to, as I said before, to link in the dependency tree in terms of DSL code. Yeah, we're not going to change that for now. So, as I said, the app main macro generates the entry point. Under the hood, it generates the app main, it calls the live design, live register functions, and it starts the application main loop. So, let's go build a slideshow. Now that we have a minimal app with a window, we can go build the UI. So, we're going to build a slideshow, and now that we have the minimal window, we can add things. We're going to create 2 buttons to navigate it with the mouse. We're going to put those buttons to the left and the right of the window, and we'll put an overlay on top of an image within the slideshow. So we're going to start by creating the buttons. In the end, this is what it'll look like. It'll be an image with 2 buttons. That's the end of step 2. So let's go create the buttons. Again, the code is in the image viewer repository. You can just go to step 2.1. We're going to add resources. We're going to refer to resources as dependencies in the DSL, define variables, show how the inheritance works, and we're going to use the button widget for buttons, and show how you can fill containers. So we need to add 2 arrow icons, left and right arrow, and they need to go into the resources directory. So here we have the resources directory. So we need these 2 icons, arrow left and arrow right. You can find them, of course, in the resources directory in the image viewer, a crate, or you can see yeah, just copy them from the image viewer crate, because those are all the resources that we need. And now we're going to use those resources using the DSL. And the way to reference a resource in the DSL is to type dep, dependency, and then a path using a URL-like syntax. Crate means the crate structure. So if you type crate self, it means that this path will become the path of the crate that you're compiling in. Then you say resources, arrow left and arrow right. And we're going to put them in variables. So here you can see how you store these dependencies in a left arrow and a right arrow variable. And these variables we're going to use in the UI later on. So the way to refer to a variable in the current version of the DSL is to put it within parentheses so that it is resolved as a variable. Let's talk briefly about the inheritance. Inheritance in the DSL works very similar to prototypical inheritance in JavaScript, with 2 differences. The properties are copied over at startup time, and you can override leaf properties. And we're going to in the next version of the DSL, these rules are going to change, but this is how it works right now. The syntax is very simple, just like JavaScript. You define an object like this. This defines an object named foo, and if you then type this, that inherits from foo and overrides the properties that you put in this object. So yeah, all of our components are implemented this way. So button is essentially an object that is connected to a Rust system, and then you, whenever you see something like that, this in the DSL code, it means inherit from that object. So here you see that these two are inherited, and the end result of the properties will be this. This is a more complex example, but it's not super useful to dive into this deeply. We're just going to show you how to make your own button. So here we're going to make a slideshow button, and it derives from button. This is the syntax how to derive from a base component. If you're curious what the base component looks like, you can look in Makepad, the Makepad framework repository, and then this would be the button. Here you can see all the style properties that are on the button, which is shaders, color properties, and they're all overridable to style them, which is what we're going to do right now. We're going to override the style properties on the background, and we're going to change how the icon, we're going to change the icon width. So it has the following properties. We have the margin, so there's no margin around the button. We have a width. We make sure that the height fills the whole screen. And we're going to override some colors on the background and a width on the icon. So we have not specified any icon, but that's what we're going to do in the instance, because the icons are different for the left and the right button. So we're going to update the app. This code goes into the DSL, and now we're going to add these two buttons to the UI. And in code that looks like this, we have the variables, we have the button, our custom slideshow button, and then we instance the left and the right button in the window like this.
It's maybe worth pointing out that the DSL is not sequence independent, right? Like the order matters. Some people.
Yeah, so the DSL in its current form is order dependent, so that means that you need to define the button above where you use it. So you can't put it below. Like Rust is order independent, ours isn't yet. We're going to fix that though, but right now it's order dependent. So we're going to check our progress. Let's run step 2.1. Let's see. Cargo run release. Here we go. Right, so we have got two buttons with the left and right icon in it, in the left of the window. That's what it should look like. And now we're going to create the overlay. And the overlay will use the two buttons to navigate the slideshow, and we're going to put them to the left and the right. And we're going to overlay an image. So we're going to use a filler widget to push the items out in the middle. Let's see. Okay, we're going to make a slideshow overlay. Right. This is the component that is going to contain the buttons and pushes them out to the side. And so instead of putting these buttons immediately in the view, we're going to make a separate component out of that. So this also shows that in Makepad these kind of components in the DSL are very easy to create. They require barely any syntax. So now we have here the slideshow button, and then we're going to make the overlay, which is in this case a view. And then in the body we reference the slideshow overlay. And now that we have this little filler in the middle, it should push the buttons out to the side. These components are named. So you see left button equals, right button equals. And that is important because then we can reference them in Rust. So yeah, update the app structure with the slideshow overlay in the middle. And then we can run it. Let's see what it looks like. It should push the buttons out to the side. Someone told me it doesn't matter how fast your Rust compiles, and I disagree because every step recompiles everything. Yeah, so now we have a button on the left side and a button on the right side.
Does that work for everybody? Like, is everybody still like, is that off? Does that work for everybody? Is anybody able to follow? Any help needed?
Right. So now we're going to create the slideshow. We're going to structure it as follows. Let's see. Yeah, we're going to add a placeholder image. In this case, we're going to reference the placeholder image exactly the same way as we do icons. We're going to make a dependency, and we're going to define a slideshow component. So it works the same way as the overlay. We're essentially componentizing here. We're componentizing everything that we've built. So we're going to make a slideshow view that is set to overlay, and it's going to take an image, and it's going to put the overlay with the two buttons on top. And the image will take up the entire space. Fit biggest means how the image is scaled inside. Yeah, there's a few of these options in the image. And as a source, it's going to reference the placeholder. Overlay just means that you can have items flow right, so from left to right. You can have items flow down, and you can have items flow back to front, which is overlay. So it just means that every child gets the full size of the parent window back to front. Image is just a built-in image component, just like button is a built-in component. And we're going to update the app again. Now it looks like this. We have a slideshow button, and we have added a new resource reference, the placeholder. We have the overlay with the two buttons that we did in the last step. And now we have the slideshow, which is a view, an overlay. It has the image and the buttons. And now we can just instance that one directly in the app. So we're componentizing the structure. And that looks like this. Here we have two buttons and a background image. So now this is the beginning of an image viewer. So now let's go to step 3. We're going to make the slideshow interactive. And for that, let's see. We're going to use a directory of images. Let's see where we get that from. Right. We need state. in the application. We need to know which is the current image, and we need to navigate them by keyboard or mouse. So we're going to learn how to refer to dependencies in Rust, how to add state, and how to use the lifehook trait to initialize the state, because that was the life cycle trait for the application. We need to download the images, but the images are in this directory. So if you downloaded this crate, the image viewer crate, they are in the images directory. So this is why it's handy to download all of these steps, because the images are in this root folder. So you already have them if you have the image repository, image viewer repository. And then now we're going to write a little bit of Rust code to read a directory. So we're going to import some types for that. We're going to import path and pathbuff. Let's look at the step 3.1. We have a path and a path buffer. So this is just normal Rust code. We're going to look at what that does. And now we're going to load the list of images from that directory. So first off, we're going to create a state structure that is going to hold the list of images, and we're going to give that a current image so that we know where we are in the list of images. This is all relatively normal Rust code, but we're going to store that state onto the abstract. In this case, we're going to add an attribute #Rust, which means don't touch this with the DSL, and here's the state. So it looks like this in code. Where's my state? Oh, made a forward reference to it. The state is at the bottom. So we have a state struct, and then we reference that on the abstract like this. So now we have a place to store our state. We're also going to add a placeholder dependency onto the Rust struct. And this is a live dependency type. And that means that it can contain a pointer, it contains a reference to a dependency, like an image or an icon that you reference in the DSL. So the value type of, the value type of this is a live dependency. So you can store it in a live dependency type variable. And we're going to use that in this part of the tutorial. So now that we have a state struct, we have the image paths and the index on there. And that's all the state we need. So update app, and now that we have a state field, we're going to initialize it. And let's see. Yeah, we're going to do that in the lifehook trait. Let's see. So first off, we're going to fill in the placeholder value in the DSL. Here in the DSL you see placeholder : Now one thing to explain very briefly is if you see a colon in the DSL, that means that there is a Rust value backing this DSL value. So a colon assigns a value directly to a Rust struct. In this case, the placeholder value, and we reference the placeholder dependency variable here. So this is stored here. We're going to define some helper methods to initialize the state struct, because we're going to read a directory on disk. We're going to read all the entries, and we're going to store that in the state. So here you see the function load image paths. It's going to, in this case, just for the sake, clear the image paths, read a directory from a path, iterate over all the entries, and if it is a file, we're going to push that path into the vector of images. And at the end, we set the current image to 0, so probably for safety. This is the set current image function. We're going to call that when you click on the buttons. It sets the index of the image, and then it is going to use some of the Rust APIs that we have to work with our UI components. Let's see. It's explained here, so I don't want to run too far ahead of the explanation. Yeah, so this code is the way you query UI components in Rust from the DSL. So you say self.ui, which was the UI reference, right? UI was the widget ref API component, and the widget ref has, for every widget type, has a search function. That is the name of the component, like button or image or view. And it says here, search the image component named slideshow.image, which is a path. And this returns a reference to the UI component, so you can start calling APIs on it. In this case, you call load image file by path async. And that means, go load this path, but don't block the main thread. So it's using a worker to decode the images. And in this case, if the image doesn't load or doesn't have a path, if the image doesn't have a path, it's going to load an image by dependency, and it's going to use the placeholder. Apparently, this was needed. Should be, apparently we needed S-string here, but yeah. So this function updates the current image in the slideshow. Now we're going to initialize this from the code flow, and that's why we need the live hook trait. Live hook allows you to hook into the life cycle of the live traits that we have derived. So here we have the derive live. That has a life cycle, so we don't derive live hook now anymore. We're going to implement it ourselves. So we're going to implement live hook for app. And then we have this function called after new from doc. This means literally what it says, after the object has been created from the DSL document. Call this function. And in this function, this is like a constructor function for components and for applications. And here we load the image paths. As you can see, there is a relative path in here. So in this case, the images directory is 2 hops up from the repository. You can change this path to where you put the images in your tutorial. You not only you have to change this path, otherwise you get an error on the command line that it could not open the directory to read the file. So that's important. If you get an error, you need to change that path to something that points to this images directory. So let's check what our progress is. We're going to run cargo run on 3.1. 3.1. Cargo run release, and that should give us at least the first image is showing. The first image from the directory is showing in the application. Now we're going to start handling events. We're clicking on the buttons and we're going to cause the images to flip around. And we're going to talk about how event handling and actions work. how the keyboard focus works, and we're going to look at the match event trait. So let's talk briefly about how events and actions work. An event is a notification that the user did something interesting. For instance, the user clicks the mouse button and it dispatches the mouse down event. An action is a notification that something happened to a widget. A button emits a clicked action. So you can see it as like events go into the UI tree and actions flow out of the UI tree. A mouse down goes in and a button emits a clicked and it goes out of the UI tree. These are the two main mechanisms that things function. Generally, if you work with widgets, you don't really do anything yourself with events, except for pass them down, but you only use actions. The event bubbles down and the action bubbles up from the widget. And widgets higher up in the tree can then respond to that action. Also, let's talk briefly about keyboard focus. Widgets generally respond to keyboard events only if they have keyboard focus. You have to, like a text input, for instance, generally just grabs the focus when you click it, or when you press tab, it switches to the next text input. And we're going to also do some keyboard events, arrow keys. But in this case, we're not going to grab it globally, but we're going to listen to it on the overlay. So that means you have to click it. We're not setting the keyboard focus with code. So we're going to make some modifications to the slideshow button and slideshow overlay. Right. We're going to say that the buttons don't grab keyboard focus. And okay, I'm going to capture overload on the overlay. Hold on. My co-founder wrote a tutorial. I didn't write this myself, so I'm wondering why he's doing that. Right, okay. Yeah, so if we set capture overload on the overlay, that means that even though the button has captured the mouse down, the overlay can also capture the mouse down, and we're going to use that to set the focus. We're going to define some more helper functions in the code as well. We need the number of images. In this case, that is just the length of the image path vector, so we have a little helper function for that. We're going to make a next and previous image function, which is very simple. It just looks at the current image, subtracts one, or it adds one if it fits in the number of images list. So now we're going to wire all this code up to event handling when you click a button. For that, we're going to use the match event trait. Match event trait is really just a helper that splats out events into essentially a trait with a lot of default implemented and overridable functions. So we're going to call match event in the app main here. And then we're going to implement match event for app. And now we have a method that we can override called handle actions. So I told you that events go down into the tree and actions go up. It's a little bit odd, but the action will be readable in an action event. So the actions actually bounce down and then they can bounce back in via the actions event. Here we handle that event so to get access to the actions. And that means that we can keep a very flat code flow where now we can handle button events. So in this case, we have this block of code. as you can see, we're using the same kind of query function as we used for image, self.ui.image, self.ui.button. And then we give the identifier of the button that we want. And then you can check whether this button was clicked on the actions array. So that's what this function does. This is different from a lot of UI frameworks that send you a callback, like on clicked, right? They send and then the callback usually is a closure, and that means that it needs to lock the UI, so the data. So it needs to have a ref cell or an RC or an arc or whatever to the data. And I find that to be tedious with Rust. Therefore, we have inverted the model in Makepad so that you query the UI and then check. So this is like a polling. It polls the components to ask if it was clicked. And for that, you use a query and the clicked method. And then just like a callback, except now it's just an if, so it doesn't need to lock any data. The borrow checker does not give you any problems. You can do the thing you're supposed to do. Go to the previous image or go to the next image. And in this case, we also do the keyboard handling. In this case, it's an arrow left and arrow right. And we check that on the overlay view. So here we have both keyboard handling and button handling. So let's have a look what that looks like. Let's have a look what that looks like. Now we should be able to switch images with both the buttons, and if you click on the center image with the arrow keys on your keyboard. Okay. So now we're going to build the image grid. The image grid for the image viewer, because we have done the overlay now where we have the image and the buttons and the keyboard handling. Now we're going to show a grid of images. This requires us to do some work on procedural UI generation. So we're going to write loops and we're going to generate lists of images based on code because we have the images in a data structure. And we're going to make a grid, so we're going to make a list, we're going to make a list of lists. We're going to make a vertical list of horizontal lists. And it's going to look something like this in the end. So let's get started. So the goal is to build an image grid, and we're going to make an image grid item. That is the item in the image grid. And it looks something like this. It has a width and a height. It has an image, and in this case it has a placeholder. And we're going to essentially start over a little bit in terms of what the application shows. We're just going to show the image grid item. And the image grid item is now looks like this. It's just going to be a single image that is showing the image grid item component. Here we see the image grid item, the single image that we have defined as image grid item, and it looks like this. 0.1 image grid item. And it's at the top of your DSL, so you leave all the slideshow stuff in there, you just add a new image grid item. And then we threw out the slideshow overlay, and we're just referencing the image grid item as a test. So that's great. Now we're going to create the row. So we're going to start looping and create the row. In Makepad, that is a little bit, I would say, tedious, and we are working to fix this in a much more convenient way. But for now, this is the way to create a looped list of images using the Rust API. And for that, we're going to use the portal list. The portal list you should imagine as an infinite scrollable list of items. And Rust code is going to provide you those items. So instead of everything being in the DSL, we're now going to write a little loop in Rust that is going to draw these things. So we make a portal list, and the portal list in this case goes right, because it's a horizontal one. Well, this is not super nice, but we're going to hide the scroll bar by changing the color to transparent, because in the version that we put online, we didn't have a hide function. But that should now be fixed, but anyway, it's still in the tutorial, so you can ignore this. And then for the portal list, we need to set a template. So the portal list can instantiate objects in the DSL, but it does need to know the name of them. And it doesn't look into the entire DSL document. The portal list only looks into itself. So if you want to instantiate something in a portal list, you gotta give it a name here. In this case, we're going to say, hey, item is image grid item. So, so portal lists are essentially a very efficient way to draw very, very long lists. And almost everything in Makepad that uses some kind of large set of data, like here, the news feed, all of this stuff is portal lists, right? So this is just an infinitely scrolling list. Portal list is a very important widget, and we use it all over the place, especially for like mobile endless scrolling UIs and stuff like that. So what we're going to do is we're going to make a special component for a row of images, a Rust component. Since we have to override the Rust code that generates the widgets, it is useful to do this as a component. We could also do it on app, but yeah, it's more useful the moment you need to do custom drawing code to generate a component. So yeah, as I said, the templates are referenced on the portal list. Let's see, we're going to update app again. Let's go to app of step 4.2. Right. So we now have an image grid row that is a component, right? So it's referencing again those double curly things. And if you look at the Rust code, it is at the bottom of the file. You see that we're going to define an image grid row component. Just like app, it's very similar to app. We say derive, live hook, except now we also add widget. So, or component, like a widget. We're going to make this a widget component. And because we don't want to define all of the stuff you need to make a view, we're going to essentially deref from view. So in Rust, you don't have extend, or you cannot inherit from another object. But they have a little loophole. It's called the deref trait. The deref trait, if you set a deref to a subproperty, that means that if Rust cannot find a name on your struct, it will look at the deref of that struct. And with that trick, you can still somehow do a little bit of inheritance. And this is a very, very common way that people building Makepad applications create a custom component. They deref to view, and then it magically already works. Then you implement a widget for the row, and this is where, I think it's a little bit verbose right now. We're working on it, so just bear with us for a little bit. This is where we custom draw the items that are in the list. And here you see the signature of the two main functions for all components. All components have a draw walk method, which means, please draw yourself with the context, scope, which we're not going to talk about right now, and the way walks are layout elements, and they specify essentially the size of the item that needs to be drawn. In this case, Makepad supports resumable drawing, so that means that you can have a component deep inside the UI structure that needs some data, or you want to custom draw it, and these are called draw steps. And here you can see how we use that to draw the portal list. So you have to imagine Makepad is drawing the UI, it's drawing the UI components, it's going over the tree, and then it hits the portal list, and it realizes, hey, the portal list needs custom code to draw it, right? You need to have a hook, essentially. But here is the same problem that you have when you have on-click. You kind of need a callback from the portal list. And if you do that with a closure, you're going to have the same problems as you have with on-click function. So this is a way that we have allowed an unlocked hook. Essentially, you can you get a reference to the portal list, and you can create a little custom draw function for it without having to use closures or other stuff. So that means that you can just reach your data. And here, let's see where the tutorial is so I don't run too far ahead of it. Let's see. Yeah, so we implement the widget trait. Yeah, this is a little bit confusing. We have called it derive widget, and then you still have to implement the widget trait. Yeah, that's a naming convention that we broke, but the widget derive actually derives everything around the widget trait that is needed to implement it. So yeah, otherwise we would have had to call this widget node or something, because widget node is the real trait that is implemented, and this is just the name for your wrapper. So just go with that for a little bit. Yeah, so we were talking about the draw walk method. Here we have the draw walk. Let's have a look. So draw walk returns a specialized result. So draw step is actually a type alias to a result. And the reason that it's a type alias to result is that Rust forces you to handle results. You cannot forget to use a result in Rust. So this forces you to realize that this is a resumable function. And here you see while, the while loop around draw, and that means that every time this draw walk returns an item that needs custom drawing, the code assumes that you're going to call it again to resume. So that's why a result is returned, so that you can never forget to call it again. So yeah, you have to do this loop to get your portal list. And yeah, because Rust is strongly typed, this kind of code gets a little bit messy as you have to cast it, essentially upcast it to your portal list. And here it says, so every item, this could be any widget, right? So you don't know what kind of widget it is. Then you say, oh, assume it's a portal list, and then you borrow it. And if it was a portal list, this will be a reference to the list, a borrowed reference to the list. So now I can call this as a normal Rust object and use the API. So to draw a portal list, you have to give it at least an idea of how long it is, how many items does it have. And yeah, that's needed because otherwise we can't do any kind of scrolling or any kind of limiting. And then we're going to loop over the list with next visible item. And this is because it's a virtual viewport, right? The moment the viewport is full of items, the next visible item will stop. So you loop over the next visible item, and then we're going to call the template creation. As I explained before, a portal list has, where's my portal list? A portal list has a reference to the item you want to instantiate. And this is the template of the item that you're instantiating. And here we say, hey, list, instantiate the item with this index and this template. And then you can draw the item in the list, and we have code of data-driven UI. As in, it's all immediate mode. So I am not creating a DOM tree here. I'm just having the portal list draw the items that it can see. Yeah, you might also see the live ID macro. So all the IDs that you see here, these names, right? They don't have a Rust representation. Like you need to use this little macro to get a Rust representation of the identifier. So then you can talk to the DSL structures. So just like with app, we have to forward our handle event to the UI. In this case, we have a view. So that's what we do here. Now let's check our progress. We're at 4.2. 4.2. Oh. Let's see where we are. Here we go. Now we've got 4 images, and they're the list is still doing pull down. Still doing pull down, so you can turn that off as well. Just ignore that. Now we're going to create the image grid, right? So now we have 1 row. We can create a grid. And we're literally going to do the same thing. We're going to create a portal list of rows that is flowing down. Also hide the scroll bar. And then instead of an item, we're going to reference the image grid row. It's exactly the same as we've done for the image grid row. We're now going to make an image grid component and call the row items. So this just creates exactly the same code as we have done before, except now we're going to loop it vertically. And that's pretty much the same. This is, by the way, not the ideal way to create an image grid. We really just need an image grid component, because that is much better than having 2 nested portal lists. But for this tutorial, we used 2 portal lists. So now we're going to make the image grid dynamic. We're going to use the data that we've loaded from our disk for the previous image viewer overlay, Now we're going to use the state struct. And for that, we are going to have to define a max images per row on the state. And let's see, going to add a few helper functions. The number of rows, the first image for a row, and the number of images for a row. I'm not going to go through the detailed math here, but yeah, I just assume that this works. And yeah, so we're going to update the state. Now we cannot derive from default anymore. We're going to implement default for state and provide max images per row, hard-coded here to 4. This is the default derive. If you derive default, everything is default, but now we have to set this value, so we're going to implement our own default own default trait. So now we're going to talk about how we can get to the state from the widgets, right? Because the widgets are now components that live in the UI tree. So how do we get the state that lives on app down into the components? For that, we're going to use the scope. And the scope is essentially a struct that has a couple of borrowed fields that you can put any data on. Any data that you want, you can put on there. And this is also why you see that the code flow always flows down, because you can use essentially the scope to pass data down into the UI tree. So we're going to modify the app main. Let's see, I think we're at 5, right? Yeah. I'm going to modify the app main to pass in the state into the UI tree. So here we say, let's make a scope with data, and the data is a state, and we're going to pass that scope into handle event. So now the data of the state flows into the UI tree. And this is a very useful method. We use that all over the place when we're componentizing a larger application. You pass data, you pass your app state this way with scope. And now we have to pluck that data off the scope in the component. So in the image grid, we're going to pluck that state object from the scope. And you can do that with scope.data. In this case, we're getting the mutable data. And because it is this is a getter for an any type, it has to cast. It has to do a type cast for what is in this scope component to this object. And the reason we use like an any cast is otherwise you would have generics all the way down of your UI tree, and that is just not useful. So this is how we can get the state back if you're on the UI component. And now we can start reading that state to draw the rows. In this case, we're going to use the number of rows for the length of the list, and then skip it if so this is one maybe odd thing. You set the range here to the number of rows. However, the list, the portal list keeps going when it hasn't filled the screen. And the reason for that is that we often do things like this, right? Like if you see, here you see a list with even odd coloring, right? Like these bars are essentially filler. These are also components, but they're filler. And these filler components, so this is also a portal list. My log viewer is a portal list. And it has one item, but then it keeps going until you tell it to stop. And that is a way to draw these filler items. Maybe we should make that optional, but this is why this check is here. So because it will keep going, so you can fill out the list to the bottom. That's why this continuous here. So yeah, as I showed, we fetch the state, set the range, This is the check that's necessary because it only shows the minimum number of items. And then we're going to create a new scope, but we're going to also add in the row index. So a scope is a little bit of a flexible object. It has a few fields that you can override, and we've added a few fields that are very common. One of them is a U size, because this is a very common thing. You have, the scope actually has 3 fields. It has a mutable field, a mutable any field, immutable any field, and a U size, which is often used for indices into arrays. So here we create a scope with the data, which was the state that we already had, and we're going to add in an index and then pass that down into the row. So now that we have our data going into the widgets, we can update now the row widget. We can fetch the state just like we did in the grid, and then we can fetch the row index by saying, hey, can you, oh, he's not using the U size, he's using the immutable. So this is a cost to a U size, so also fine. You can, it doesn't really matter. You can use a scope to store anything on the mutable, immutable, and U size field in any way you want. In this case, he's using the immutable. The mutable one is called data. The immutable one is called props. And now we update the drawing loop here to draw the image from our set of paths. In this case, we're going to load the image file by path async. So yeah, this is a little bit why Rust is, yeah, you know, a little bit verbose for UI. This is not really, most of this code is not really a Makepad thing. This is just how Rust, how much things you need to do for Rust in this case. So here we load the image, and then let's see. Yeah, we check that the image is correctly loaded, and now we should see a grid of images appear. Yeah, it's just step 5. So here we have now an image grid that is virtual viewport. If you have many images, it should just be loading on demand and quite efficient. So if you have, technically this setup should scale pretty well. Right, so we have our image grid.
Okay, Rick, so do you want us to take a...
Yes, we were at making the image grid. Also, over the break, I was notified that we were using, in the later examples, using a lot of CPU. One of the reasons is that the example that we're going to do with animation is doing it in a kind of a dumb way so that it keeps repainting. And that is not, of course, how you would build a widget that just keeps repainting, because that just wastes battery. Another one is that our memory usage is a bit high. I just did a profile, and yeah, unfortunately, a good chunk of that memory is Chinese fonts. We are defaulting to a couple of really large fonts. They're literally 40 megabytes or something just in memory for one font file, and there's 2. And then there's the texture atlases. So we're already using like 80 megabytes of RAM just for the fonts. And that is an unfortunate side effect of rendering everything yourself. We have some ideas to reduce that a little bit, but or maybe try to leave the TTF file on disk and memory map that so that it doesn't have to go into RAM. But yeah, so those are known issues. So just so you're aware of it. Making an image grid, where were we? I think we had the image grid working, so we'd finished number 5. And now we're going to switch between the image grid and the slideshow. So for that, we're going to use the page flip widget, which just allows you to toggle between two child widgets. So we're going to make it possible to switch between the slideshow and the image grid. For that, we're going to add just a button in the menu bar that allows you to click to slideshow. In this case, we're going to make a menu bar that fits the whole width and fits the height. This means that the button in this case defines the height of this view. We're going to right align it. So in Makepad, alignment is done using X and Y properties, and these are floating point values between 0 and 1. 0 means all the way to the left, 0.5 means the center, and 1.0 means all the way to the right. So it's a little bit more expressive than you would get with just left, center, and right, although it's rare that you ever need to use anything but left, center, or right. But this is how you define that. We're going to make a new component to wrap the menu bar and the image grid, which is the image grid that we just made and the menu bar that we just defined above it. And then we're going to update the app to have the image browser. So when we see that result, 6.1, hold on, I changed my viewer 6.1. See what that does. And now we're going to use the page flip widget to flip between those two components. Right, so now we have a slideshow button in the corner of the window. So now we're going to update app to have a page flip between the image browser and the slideshow. And we're going to wire up the button to perform the page flip. So in this case, now we have to add an event handler for the page flip. So in this case, the thing is called button. I don't know why, but it's called button. And we're going to query the page flip widget and then select the active page that we want to go. In this case, we're going straight to the slideshow. And let's see, this is the code, as I just showed you. You query for button, you set the active page to slideshow, and then we're going to use the escape key to flip the page back to the image browser. So let's check what that looks like. Check what that looks like. Okay, so now we have a slideshow button that switches to the slideshow, and when we press escape, we get back to the image grid. So yeah, these steps were very basic, very quick. And now we're going to add a few animations. In this case, I think we're going to add hover animations that scale the image. So here we have the animator syntax. I suggest you just copy this. It's a little bit verbose. The reason that it's verbose is that this version of the DSL, we were building a timeline animation editor for this. Now with the new DSL coming in later on this year probably, I'm going to redesign this animation to be more like you're used to from JavaScript. So just take this as it is, the animator. Essentially, the idea is that you have a state, in this case the hover state, and the hover state has an on and off state, and in the hover state you can specify the duration coming from a state. So from all states is the duration, this one. From all states is this one. And then you tell it to apply these properties. So we're going from 230 width to 265 width. And because these changes require a regeneration of the UI, a redraw, we're going to set redraw to true, which means, hold on, yeah, which means that the images will start to do something like this. Right, we hover and then the images scale up a little bit when you hover, which is a nice, nice little trick. So, yeah, we went over the animator, we went over the states, the values, apply, and so this is the basis of how most widgets are animated in Makepad, except a lot of the widgets don't use the redraw true. They actually just poke values straight into the GPU data, which will result in a lower CPU usage when you hover over components, because it doesn't need to regenerate. Now we're going to go into styling things with a shader a little bit. All of Makepad UI, you can write little shader functions to style a component. In this case, we have a Perlin noise, this is Perlin noise, shader function. It's explained in the online tutorial. I'm not really going to go into it right now, but I'm going to add the code to the slideshow button. Here you see, this is our shader syntax. It looks a lot like GLSL, and it's going to draw this noise function onto the background of the button. So yeah, I suggest just copy this code or grab the example. And because this function, let me see where it uses the time value. This function is using the time value, and the time value is something that you should actually never use in Makepad UI code, because it will cause the screen to repaint continuously. It's kind of meant as a value you use in shader toys or little examples. So when you run this example, it is going to repaint continuously, and you can see that in your GPU and CPU usage. This is not something you would do for a UI component. With a UI component, you would use the animator to animate a value and never animate it continuously. But this is just a demo of using a shader. So we're just going to run it and go to slideshow, and now you can see that there's a Perlin noise animation running on the button. And yeah, we use that in Makepad everywhere for yeah, button animations or all of the UI styling that you see in our UI, including right, like animating code folding like that. We have what is it? Even drawing the little scroll bar or this animation in the button. All of these are little shader programs that are animated using the parameters that are animated from the animator. So that's yeah, a very short introduction how you can override shader functions in Makepad. I can go into a little bit how the shader works. Not from the technical point of view, but from the point of view of the DSL. So drawBG is the shader. So if you see a view or a button or anything that has a drawBG, a draw background, this is essentially a shader block. And it has an entry point called pixel, and this pixel entry point is what defines the color of the rectangle behind the component. And this is pretty much just a shader toy. Like you can cut and paste a shader toy in here if you update the syntax a little bit and it'll run. You can just do that. So one of the examples I have here, for instance, where you can use a shader like that is here. I'll run this, for instance, my fractal zoomer example, and now I implemented that fractal zoomer with a little shader program on that draws the fractal tiles. The fractals are not computed on the GPU, by the way. They're computed on the CPU. But this is the little pixel shader, the tile that draws the fractal texture. And that means that we can live code the shader that is defining the color, just like you would be able to if it was a shader toy or something like that. So, yeah, Makepad uses shaders everywhere, and it's uses it also for simple things, like if you look at the button. If you look at the button here, well, I think maybe the snake one is also a nice example where everything is generated with shaders. In this case, using AI. But let me see if I have a nice example. Well, here's just some buttons. Let me see if I can show how the button shader is constructed. Yeah, so here's the button shader. Sebastian has been doing a lot of the shader code. So he's one of those rare designers that dares to write code.
Right, but maybe it's worth pointing out that what's in the tutorial right now is not what you would typically write in Makepad. Actually doing the stuff that's necessary for UI is far more trivial than what you see with the Perlin noise example. Yeah, so just don't let that deter you from actually dabbling with that. It's a better idea to actually have a look at the existing buttons that we have, and like the shader code that you can inspect there for buttons, for text boxes or whatever, and that's going to give you a far better idea of how these things should actually work in practice and what you need, right? It's not that hard, it's relatively accessible, right?
Right, so here you have the button, right? And this is the shader code that draws the button. The reason that it's a bit verbose is it's using a lot of these stylable parameters that you can override without having to write shader code. So you can just say border color or something like that. But now I'm going to write just plain code, right? So if you return red, your buttons become red. If you return like a mix between red and green, and you use the hover parameter, now the button becomes red and green whilst hovering over it, right? And these shader functions can also use SDFs. For instance, SDFs are distance fields, and let me do some SDFing. So this is essentially a canvas API in a shader, so you don't have to well, that's a lot of code. SDF box, SDF fill keep, yeah, right. SDF.box, no, what is it? Rect size of X, size of Y. What is the error? Oh, got 6 arguments, not enough. SDF.fill, red. Right, so here you see that you have a border radius rounded box, right? And for instance, if you want to on hover change that value between 20 and 0, you can write it as essentially a little bit of math with a blend function. And now, not 1, 0, 1. See, now the corner radius is animating as I hover over it.
That's also why it's oftentimes useful that booleans in Makepad oftentimes are actually floats, because you can interpolate them this way for animation.
Yeah, exactly. Like, so in the shader, the hover value is generally an animated floating point and not a boolean. This is how you would use an animator without continuously repainting. So yeah, but you know, it's a cool little thing, because everywhere you have a value, you could use a piece of code, right? So you could do, you know, have a gradient vertically. Now you have a gradient on your button. You could animate that gradient by, again, doing something like this. Let's say we want it to be bright white, self.hover. Right, so now we're the other way around. Maybe a bit. Right, now we have a button that has a little bit of animation going on when you hover over it. So this is a little bit of an example how you would style UI with shaders. Yeah, we use it all over the place, and I think it's really flexible and powerful, much more so than if you would do this with CSS, because there you can only parameterize essentially a vector engine, and here you can literally write a tiny inline 3D engine if you would want to style your buttons with some very specular fancy effects. So I think that concludes our part of the workshop. I think Alex is going to take over for the Molekit integration part, where AI is going to be hooked up to generate the images